Hello, dear students. Welcome to massive open online course on SWAYAM in chemistry. Myself, Preeti Kiran, PGT Chemistry from Kendriya Vidyalaya No. 1, Air Force Station, Agra. Dear students, in the previous module, you have studied about the rate of a chemical reaction, the units of rate of a reaction, average rate and instantaneous rate of the reaction, effect of stoichiometry on the rate of the reaction. Today, I will discuss and you will learn about the dependence of the rate of reaction on concentration, define rate law and the rate constant, differentiate between molecularity and the order of a reaction. First of all, let's discuss factors affecting the rate of the reaction. The rate of a reaction is influenced by number of factors as follows. Experimental conditions such as concentration of the reactants, pressure in the case of gases, temperature of the reactants or the products, nature of the reacting substances, presence of the catalyst, and now let's discuss each factor one by one. First of all, effect of concentration on the rate of the reaction. The rate of a chemical reaction at a given temperature may depend on the concentration of one or more reactants and the products. It is found that the concentration of the reactants decrease while the concentration of the products increase with the passage of time. You can see the graph, and the graph shows the variation of the concentration with passage of time. The representation of the rate of the reaction in terms of the concentration of the reactants is known as rate law. It is also known as rate equation or rate expression. Now, rate law and rate constant. In the first module, we have calculated the average rate of the reaction for hydrolysis of butyl chloride with passage of time. We found that the rate of a reaction decreases with the passage of time as the concentration of the reactants decrease. Conversely, the rate generally increase when the reactant concentrations increase. So, rate of a reaction depends upon the concentration of reactants. Let's consider a general reaction. Small a, that is the moles, and capital A is the reactant. So, using this type of notation, I am taking a general reaction. A moles of A plus B moles of B gives C moles of C plus D moles of D, where small a, b, c and d are the stoichiometric coefficients of the reactants and the products. The rate expression for this reaction is rate is directly proportional to molar concentration of A raised to power x and molar concentration of B raised to power y. This is equation number 1. Where exponents x and y may or may not be equal to the stoichiometric coefficients small a and b of the reactants. Above equation can also be written as rate is equals to k molar concentration of A raised to power x into molar concentration of B raised to power y. Now, I have introduced the proportionality constant k. Minus dr by dt is equals to k molar concentration of A raised to power x into molar concentration of B raised to power y. This form of equation is known as differential rate equation, where k is a proportionality constant called rate constant. The equation, like number 1, which relates the rate of a reaction to the concentration of the reactants, is called rate law or rate expression. Thus, rate law is the expression in which reaction rate is given in terms of the molar concentration of the reactants, with each term raised to some power which may or may not be the same as the stoichiometric coefficient of the reacting species in a balanced chemical equation. The rate constant k, also known as velocity constant or specific reaction rate, is defined as the rate of the reaction when concentration of the each reactant is taken as unity. As the molar concentration of A equals to molar concentration of B equals to 1 moles per liter, and then the rate will be equals to K. Thus, the rate constant gives an idea about the speed of the reaction. That is, a reaction with a higher value of the rate constant proceeds at faster rate. The rate constant depends upon the temperature while independent of the concentration of the reacting species. The rate law expression can be explained using the following example. 2 moles of nitric oxide plus 1 mole of oxygen gives 2 mole of nitrogen dioxide. We can measure the rate of this reaction as a function of initial concentration, either by keeping the concentration of one of the reactants constant and changing the concentration of the other reactant, or by changing the concentration of both the reactants. The following results are obtained. Now, you can see from the table the initial rate of formation of nitrogen dioxide. The data is in front of you. Now, using this data, we are going to solve the problem and understand the concept. It is obvious after looking at the results that when the concentration of nitric oxide is doubled and that of the oxygen is kept constant, then the initial rate increases by a factor of 4 from 0.096 to 0.384 moles per liter per second. This indicates that the rate depends upon the square of the concentration of nitric oxide. That is, rate is directly proportional to molar concentration of nitric oxide raised to power 2. When the concentration of nitric oxide is kept constant and the concentration of oxygen is doubled, the rate also gets doubled, indicating that the rate depends on the concentration of oxygen to the first power. That is, rate is directly proportional to molar concentration of oxygen. The square brackets represent the concentration. Hence, the rate equation for this reaction will be rate equals to K, molar concentration of nitric oxide raised to power 2 and the concentration of oxygen raised to power 1. The differential form of this rate expression is given as minus dr by dt is equals to K NO raised to power 2 and oxygen raised to power 1. Both are in the square brackets, that means the concentration terms. Now, we observe that for this reaction in the rate equation derived from the experimental data, the exponents of the concentration terms are the same as their stoichiometric coefficients in the balanced chemical equation. Now, the example number 1, you can see CHCl3, it is chloroform. When it reacts with chlorine, it gives carbon tetrachloride, that is CCl4 plus HCl. The experimental rate expression is rate is equals to K, molar concentration of CHCl3 and molar concentration of Cl2 raised to power half. Another example, CH3COOC2H5 plus water. CH3COOC2H5 is an ester and this is an example of hydrolysis of ester. What we get is rate is equals to K, CH3COOC2H5 raised to power 1 and molar concentration of water raised to power 0. In these reactions, the exponents of the concentration terms are not the same as their stoichiometric coefficients. Thus, we can say that the rate law for any reaction cannot be predicted by merely looking at the balanced chemical equation. That is theoretically, but must be determined experimentally. Before going on the further, it is very important to know the difference between the rate of the reaction and the rate constant of the reaction. As discussed above, the rate of the reaction is expressed as the speed of the reaction at which reactants are converted into products, while the rate constant is the proportionality constant in the rate law expression. Also, the rate of the reaction depends upon the concentration of the reactant species at a particular moment of time. while the rate constant is equal to the rate of the reaction when concentration terms are unity at that moment of the time. The rate of the reaction generally decreases with the progress of the reaction. On the other hand, the rate constant is a constant value for a reaction at given conditions. Now, let us discuss another concept, that is the order of the reaction. In the rate equation, rate is equals to K molar concentration of A raised to power x and the concentration of B raised to power y, where x and y indicate how sensitive the rate is to the change in the concentration of A and B. The sum of these exponents, that is x plus y, gives the overall order of a reaction, whereas x and y represent the order with respect to the reactants A and B respectively. Hence, the sum of the powers of the concentration of the reactants in the rate law expression is called the order of the chemical reaction. The order of a reaction can be 0, 1, 2, 3 and even a fraction. A zero order reaction means that the rate of a reaction is independent of the concentration of the reactants. A balanced chemical equation never gives us a true picture of how a reaction takes place, since rarely a reaction gets completed in one step. The reactions taking place in one step are called elementary reactions. When a sequence of elementary reactions called mechanism gives us the products, the reactions are called complex reactions. These may be consecutive reactions. Example, oxidation of ethane to carbon dioxide and water. It passes through a series of intermediate steps in which alcohol, aldehyde and acid are formed. The reverse reactions and the side reactions. Example, the nitration of phenol yields orthonitrophenol and paranitrophenol. Now, let us discuss and find the units of the rate constant. For a general reaction, A moles of A plus B moles of B gives C moles of C plus D moles of D. For this, the rate law will be rate is equals to K, the concentration of A raised to power x and the concentration of B raised to power y, where x plus y is equals to n is the order of the reaction. Now, K is equals to rate divided by concentration of A raised to power x, concentration of B raised to power y. Concentration upon time into 1 upon concentration raised to power n. It will be equals to concentration raised to power 1 minus n into time raised to power minus 1. And they are taking SI units of the concentration, moles per liter and time in seconds. The unit of K for different reaction orders are listed in table 2. Now, you can see for various orders the unit of the rate constant we can find out by putting it in the formula. Let me take the first example. Calculate the overall order of a reaction which has the rate expression. A part, rate is equals to K, concentration of A raised to power half, concentration of B raised to power 3 by 2. And the second part is the rate is equals to K, concentration of A raised to power 3 by 2 and the concentration of B is raised to power minus 1. Now, let me solve part A first. First of all, let us write the rate expression. Rate is equals to K, concentration of A raised to power x and concentration of B raised to power y. The order of the reaction is x plus y. So, here x is half and y is 3 by 2. So, let us add them. 1 by 2 plus 3 by 2, it gives 2. That is, the reaction is a second order reaction. Now, let me solve the part 2. Here x is 3 by 2, whereas y is equals to minus 1. So, the order is equals to 3 by 2 plus minus 1. Answer is half. That is, the reaction is a half order reaction. Another example in front of you. Identify the reaction order from each of the following rate constant. Now, you have been given the value of the rate constants, and by using the units, you have to find out the order of the reaction. The first part, the given value of K is equals to 2.3 into 10 raised to power minus 5 liters per mole per second. And the second part is given, K is equals to 3 into 10 raised to power minus 4 per second. Now, just by checking the units, the first answer is the unit of the second order rate constant is per mole liter per second. In this case, the K is equals to 2.3 into 10 raised to power minus 5 liter mole inverse second inverse. Hence, it is a second order reaction. The unit of the first order rate constant is per second. So, by comparing this, second part has been given 3 into 10 raised to power minus 4 per second. So, unit matches the first order reaction, hence it represents a first order reaction. Now, again another example for you. Find out the order of a reaction and the units of the rate constant in the following reactions. Also, state the order with respect to each of the reactants. The equation is CH3CHO, that is ethanol, it gives methane CH4 plus CO, that is carbon monoxide. Now, the rate law is rate is equals to K, the molar concentration of CH3CHO raised to power 3 by 2. Another equation, carbon monoxide plus Cl2 gives CoCl2. For this rate has been given, the rate is equals to K, concentration of carbon monoxide raised to power 2, concentration of Cl2 raised to power half. Another equation, nitric oxide plus O2 gives 2NO2. And for this rate has been given K, concentration of NO raised to power 2 and concentration of O2 raised to power 1. Now, let me solve each part one by one. First of all, part A, rate is equals to K, concentration of CH3CHO raised to power 3 by 2. Order with respect to CH3CHO now will be 3 by 2, or you can say 1.5. And the overall order of the reaction is equals to 3 by 2 equals to 1.5. Units of the rate constant K is equals to moles per liter raised to power 1 minus n per second. Here n is equals to 1.5. Therefore, units of K is equals to moles per liter raised to power 1 minus 1.5 per second. It will come out to be mole raised to power minus half, liter raised to power half per second. Part B, rate is equals to K, concentration of CO raised to power 2, concentration of Cl2 raised to power half. Order with respect to carbon monoxide, that is CO, is 2, and the order with respect to Cl2 is half, that is 0.5. The overall order of the reaction is 2 plus half is equals to 5 by 2 equals to 2.5. The units of the rate constant K is equals to moles per liter raised to power 1 minus n per second. Here n is 2.5. Therefore, the unit of K will be moles per liter raised to power 1 minus 2.5 per second. So, it comes out to be moles raised to power minus 3 by 2, liters raised to power 3 by 2 per second. Now, part C, the rate is equals to K, concentration of NO raised to power 2, concentration of oxygen raised to power 1. Order with respect to NO, that is nitric oxide, is 2 and the order with respect to oxygen is 1. The overall order of the reaction is 2 plus 1 is equals to 3. The units of the rate constant K is equals to moles per liter raised to power 1 minus n per second. Now, just putting up the value of n, here n is equals to 3, therefore, units of the K is equal to moles per liter raised to power 1 minus 3 per second. After calculating, it will come out to be mole minus 2 liter square second inverse. Now, the molecularity of a reaction. Another property of a reaction called molecularity helps in understanding its mechanism. The number of the reacting species like atoms, ions or the molecules taking part in an elementary reaction which must colloid simultaneously in order to bring about a chemical reaction is called molecularity of a reaction. The reaction can be unimolecular when one reacting species is involved. For example, decomposition of ammonium nitrite NH4NO2 gives N2 plus 2H2O. Biomolecular reactions involve simultaneous collision between two species. For example, dissociation of hydrogen iodide. 2HI gives H2 plus I2. Now, trimolecular or termolecular reactions, they involve simultaneous collision between three reacting species. For example, 2 moles of nitric oxide reacts with 1 mole of oxygen to give 2 moles of nitrogen dioxide. The probability that more than 3 molecules can colloid and react simultaneously is very small. Hence, the reactions with the molecularity 3 are very rare and slow to proceed. It is therefore evident that the complex reactions involving more than 3 molecules in the stoichiometric equation must take place in more than one step. For example, KClO3 plus 6 moles of ferrous sulfate plus 3 moles of sulfuric acid gives 1 mole of potassium chloride plus 3 moles of ferric sulfate plus 3 moles of water. This reaction, which apparently seems to be of the 10th order, is actually a second order reaction. This shows that this reaction takes place in several steps. Which step controls the rate of the overall reaction? The question can be answered if we go through the mechanism of the reaction. For example, chances to win the relay race competition by a team depend upon the slowest person in the team. Similarly, the overall rate of the reaction is controlled by the slowest step in a reaction called the rate determining step. Consider the decomposition of hydrogen peroxide, which is catalyzed by iodide ion in an alkaline medium. Now, the equation is in front of you. It is a decomposition reaction of hydrogen peroxide. It gives 2H2O plus O2 in alkaline medium and iodide ion is a catalyst. The rate equation for this reaction is found to be minus D molar concentration of hydrogen peroxide divided by dt equals to K concentration of H2O2 and concentration of iodide ions. This reaction is first order with respect to both hydrogen peroxide and iodide ion. Evidences suggest that this reaction takes place in two steps. The first step, H2O2 1 mole reacts with iodide ions to give H2O, 1 mole H2O plus 1 mole of IO minus, where IO minus is a hypoiodide ion. In step 2, hydrogen peroxide now reacts with IO negative hypoiodide ion to give 1 mole of H2O plus 1 mole of iodide ion plus oxygen. Both the steps are bimolecular elementary reactions. Species iodide ion is called as an intermediate since it is formed during the course of the reaction, but not in the overall balanced equation. The first step, being slow, is the rate determining step. Thus, the rate of formation of intermediate will determine the rate of this reaction. The detailed description of the various steps involved in a reaction is known as the mechanism of a reaction. We have to keep this in mind that each and every step involved in a reaction proceeds with different rates. Only the slowest step of the reaction depicts the overall rate of the reaction. In cases of the complex reactions, the molecularity of the overall reaction in general has no significance. Thus, from the discussion till now, we conclude the following. First, The order of the reaction is the sum of the powers of the concentration terms in the rate law expression, while molecularity is simply the number of the reacting species. Order of a reaction is an experimental quantity. It can be 0 and even a fraction, but molecularity is a theoretical concept and it cannot be 0 or a non-integer. Point 3 is order is applicable to elementary as well as complex reactions, whereas molecularity is applicable only for elementary reactions. For complex reactions, molecularity has no significance. For complex reaction, order is given by the slowest step. On the other hand, molecularity of the slowest step is same as the order of the overall reaction. Order of the reaction depends upon the experimental conditions like temperature and pressure, while molecularity of the reaction does not. It is a very frequently asked question that differentiate between order and molecularity. Let me discuss few examples. For a reaction A plus B giving products, the rate law is given by R is equals to K concentration of A raised to power half, concentration of B raised to power 2. Then what is the order of the reaction? Let us find out. The order of the reaction is the sum of the powers of the concentration terms in the rate law expression. Here we have rate is equals to K, A raised to power half, B raised to power 2. Therefore, just adding them, half plus 2 gives 5 by 2, thus the answer is 2.5. Let me tell you children that for finding out the order of the reaction, you need to write the rate law expression. Now, the next example in front of you, the conversion of the molecule X to Y follows second order kinetics. If the concentration of X is increased to 3 times, how will it affect the rate of formation of Y? The reaction is X giving Y. It follows second order kinetics. Therefore, the rate equation for this reaction will be given as rate is equals to K concentration of X raised to power 2. Now, let the concentration of X, that is molar concentration of X be small a moles per liter. Then the rate of reaction is rate is equals to K small a raised to power 2. So, it will become K a raised to power 2. Now, if the concentration of X is increased to 3 times, then the molar concentration of X is equals to 3 into A moles per liter. Therefore, the rate of the reaction will be the new rate will be equals to K 3A square. Now, it will become 9 K A raised to power 2. Hence, the rate of the reaction or the rate of formation of the Y will increase by 9 times. What simply we have done? We have just put the values and how much time the rate of the reaction is increased. Now, again I am taking an example in front of you. For what type of reactions the rate constant shall have the same units as the rate of a reaction? It is for the zero order reaction. Now, let me summarize what we have studied in this module. In the first module, we have learnt about the rate of the reaction. In this module, we learned that the number of the factors such as the temperature, concentration of the reactants, catalyst affect the rate of a reaction. It was observed that with the passage of time, the concentration of the reactant decreases while that of the products increases. Also, the rate of the reaction decreases with decrease in the concentration of the reactants. The mathematical representation of a rate of a reaction in terms of the concentration of the reactants is given by rate law. It has to be determined experimentally and cannot be predicted. The proportionality factor in the rate law is known as the rate constant. The rate constant and the order of reaction can be determined from the rate law or its integrated rate equation. Order of a reaction with respect to a reactant is the power of its concentration, which appears in the rate law equation. The order of a reaction is the sum of all the such powers of the concentration of the terms for different reactants. The order of a reaction can be 0, 1, 2 or any non-integer. Molecularity is defined only for an elementary reaction. Its values are limited from 1 to 3. Whereas order can be 0, 1, 2 or 3 or even a fraction, molecularity cannot be 0 or a non-integer. Molecularity and order of an elementary reaction are same. Many reactions occur in a number of steps that make the overall mechanism of the reaction, and the rate of the reaction is determined by the slowest step of the reaction. So dear children, today we have studied all this about the order, molecularity, rate law and the rate constant. These are very important topics from the chemical kinetics as the examination point of view. You get many numericals on this. I hope you have understood all the concepts very nicely. Thank you.